Hello and welcome to helpyourmath.com. In this video, dealing with the fundamental counting principle, we're going to look at factorials when we're dealing with some repetition. So recall a factorial, if we have n factorial, that means that we multiply n by every integer, positive integer factor that's smaller than it. So it would be n times n minus 1 times n minus 2, so on and so forth, times 3 times 2 times 1. That's what a factorial is. We're going to look at some applications where we deal with a little bit of repetition. Before we get into that though, I just want to review simplifying fractions. So how would we simplify 9 over 24? We're going to do this the more arithmetic way and not the, look, they're both divisible by 3. What we're going to say is that 9 is the same as 3 times 3, and 24 is the same as 8 times 3. So we're just going to physically write it out. So 9 over 24 is equivalent to 3 times 3 over 8 times 3. And then I see, look, there's a common factor, and we end up with 8 over 3. So a little bit longer than what we normally do, but just to help us in a second. So to simplify fractions, we divide out common factors. And factors are the things that are being multiplied to each other, right? So 3 times 3, the factors are 3 and 3. 8 times 3, the factors are 8 and 3. Okay, we're going to keep that in mind. Now, we're going to look at simplifying factorials. So we have these factorial fractions where the numerator and denominator are both factorials. We want to simplify these in the simplest way possible. So one thing we could do, which is not the simplest way, is to write the whole thing out. 8 times 7 times 6 times 5 times 3 times 2 times 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we can say, look, common factors, hooray, hooray. And we end up with 8. But that was more time than I felt like using to simplify this. What I'm going to do instead, so remember the factorial is just the number that you were starting with, the number that's given, times every integer, positive integer, smaller than it. So what we can say instead is if I start writing out 8 factorial, I could write 8 factorial as 8 times 7 factorial, right? Because that's the same thing. That's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then if I look at the denominator, look, I have a 7 factorial down there too. 7 factorial is a factor of both the numerator and denominator, so I can cross those out and end up with 8 in a much quicker way. So what we might do instead is just write out whichever one is a bigger factorial, so 5 is bigger than 2 in the next example, write out 5 until you get to that other factorial and then stop and write it as a factorial. So I'm going to expand 5 factorial to 5 times 4 times 3, and then I'm going to stop at 2 factorial because that matches what I have in the denominator. We cross those out, and now what we're left with in the numerator is 5 times 4 times 3, which is 60. Okay, one more. 11 factorial over 8 factorial. So I'm going to start by expanding 11 factorial. That would be 11 times 10 times 9, and then I get to 8. I say, wait, I'm going to stop and just leave it as 8 factorial because that's what I see is a factor of the denominator. So then I can cross those out, and now what I have left is 11 times 10 times 9, which would be 990. Okay, we're going to make this a little more challenging just because I can. And it also does say without a calculator, except I think the first one we're going to want to use a calculator. Right? Because I don't. So let's think about this. Let's pause. You try it. Tell me what you come up with. Did I get you to talk to your computer? Did I? I don't know. I have no way of knowing, so hopefully I did though. Okay, so I'm going to expand 18 factorial, but where am I going to stop? I'm going to stop at 14 factorial. So I'm going to say 18 times 17 times 16 times 15 times 14 factorial. Now I have a common factor in the numerator and denominator of 14 factorial. And now I want to multiply. Let's get our calculators handy. That'd be 18 times 17 times 16 times 15, which would be 73,440. Okay, for the second one, we have a little bit of work to do first. We need to say, wait, I know what 15 minus 13 is. That's 2. So now what we have is 15 factorial divided by 13 factorial times 2 factorial. How do you decide how far to expand 15 factorial? Well, I would stop as soon as you reach one of the factors of the denominator. So I'm going to say 15 times 14, and then I'm going to just write 13 factorial because now I know that's going to simplify with the 13 factorial in the denominator. So I cross those out, Now I'm going to expand the denominator, but there's not much to expand. It's just 2 times 1. The 1 we don't have to worry about. The 2 will simplify with the 14. That would be 7. And then 15 times 7, I believe, is 135. Yeah, that seems right. Nope, it's not right. Let's try that again. Maybe I shouldn't trust my brain and just trust the calculator. 105. That looks better. Okay. And we end up with 105. For the last one again, I'm going to stop when I get to the first factor of the denominator. So I'm going to go on and expand 12 times 11 times 10. But then I see a 9 factorial in the denominator, so I'm going to leave it 9 factorial. Now, what I might do, just to save myself some time, is I'm going to leave 9 factorial as is, because I know that's going to cancel with this 9 factorial. But I'm going to go ahead and expand 3 factorial and 2 factorial, just because I need to know what those factors are. So now I have a factor of 3, a factor of 2, I don't really care about the ones, and another factor of 2. Well, 3, 2, and 2, you can do this in one step or multiple steps, but 3 times 2 times 2 is 12. So I'm going to just take all of those and just cross out the 12 with it, because those will all cancel. Right, you can, if you do it in 3 steps, you can do it in 3 steps, that's fine. But what we're left with is 11 times 10, giving us 110. Okay, why did I just go through all of this? Because sometimes when we're doing factorials, we hit a snag. So you might recall from the previous video, I already forget what it was, but we looked at, I think it was PAL. How many ways could we arrange the letters of PAL, P-A-L? Well, there's 3 possibilities for the first letter and 2 for the second and 1 for the last, so there would be 6 total. But what about POP? So POP, we could have, well, POP is one option. We could have P-P-O. We could have O-P-P, and that's it. Because if we try to do anything else, it's just going to end up being repetition of what we already had. The P's are the same. So in this case, there's only 3 ways to arrange these letters. Why is it not 6? Because of the fact that the P repeats. So we need to come up with something here to figure this out, because I don't want to have to sit here and list combinations, because let's look at the next example. We have the letters Poppy, P-O-P-P-Y. How many ways could these letters be arranged? I want you to pause the video, make a prediction, and see if your prediction was too high, too low, or just right, based on what we know about factorials and the fact that there is some repetition. Ready, go. Okay, what'd you come up with? Well, let's see. So first we're going to list them out, and then we're going to talk about a shortcut, because obviously listing is not going to be the most productive use of our time. Okay, so we could have, well, Poppy itself, fine. And now let's see, let's move the O to the front. So we have O-P-P-P-Y. And then I'm just going to move the O around. So we're going to have, but I'm not going to put it second again because we already had it second. Then we have this. Then we can have it fourth. We could have it last. Y-O. Hey, don't disappear on me. The Y could be in a different spot. Oh boy. So then we could have Y. Ooh, gross. Y-P-P-P-O. Y-P-P-O-P, Y-P-O-P-P, Y-O-P-P-P. Okay, I think we get the idea. There's going to be a lot. And if we think about if the letters were all unique, there would be 5 factorial and it would be 120 different combinations. I don't want to sit here and list out however many it is because this is going to be too much. So here's what we do. Here's how we deal with the repetition. We know that the total, if they were all different letters, would be 120, but they're not all different letters. So what we do is we actually say it's going to be the total possibilities if everything was unique, and then we divide the repetitions. So there's 3 P's, so we would divide out 3 factorial. There's 1 O, so we can technically divide 1 factorial, and then there's 1 Y, so we can divide 1 factorial. Obviously, you don't need to include these because these are just 1, which doesn't do anything. The important thing is getting any letters that do repeat and using that. So then it would be 5 times 4, and I'm going to stop at 3 factorial over 3 factorial. I was close. There was only going to be 20, but I didn't feel like really finding them. So there would be 20 unique arrangements of the letters P, O, P, P, Y. Okay, so we pretended like I did the whole thing because I chose not to. So in listing arrangements, we have to consider repetition. Normally with no repetition, there would be n factorial ways to arrange n objects, letters, people, troll dolls, whatever. When there is repetition of some of the objects, then we would say the number of ways to arrange n objects, letters, people, troll dolls is n factorial over n sub 1 factorial times n sub 2 factorial, where n sub 1 is the number of one kind, so that was like the number of p's. N sub 2 is the number of o's, n sub 3 is the number of y's, so on and so forth. Okay, so let's put this to the test. How many ways can the letters of lollipop be arranged? So first, let's count the number of letters. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 letters in lollipop. So if they were all unique, there would be 8 factorial combinations. But there's not. So now we have, let's see, L, there's 3, O, there's 2, I is 1, and P is 2. So what we would need to do is we would need to divide out 3 factorial times 2 factorial times 1 factorial times 2 factorial. And again, we can ignore this one. If you don't want to include it, you don't have to, and that's fine. Okay, so now let's expand. That would be 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial times 2 times 1 times 2 times 1. And again, if you don't want to include the ones, you really don't have to. Well, in the denominator, we have 2 times 2, which is just the equivalent of 4. So I'm going to go ahead and just say those make a 1. And then what we're left with here is 8 times 7 times 6 times 5 possible combinations or arrangements of the letters of lollipop. So if we calculate this, we end up with 1,680 combinations, or arrangements, excuse me. Aren't you glad I didn't ask you to list all of the possible arrangements? Whew, that would not have been fun. So there would be 1,680 arrangements of lollipop. Okay, 2 more examples, I think. Yes, 2 more examples. How many ways can Sheila arrange the textbooks on her shelf if she has 9 textbooks, including 3 identical mathematical idea books, 2 identical copies of Hop on Pop, and we assume the other 4, so that's only adds up to 5. And the other 4 are just whatever. One's biology, one's chemistry, one's Spanish, and one's economics. I don't know. Okay, so it's just saying that we do have some repetition, but not everything is repeated. So if there's 9 textbooks, that would be 9 factorial. And then we would want to divide out the repetitions. There would be 3 factorial for the mathematical ideas books and 2 factorial for the Hop on Pop books. And then everything else would just be 1 factorial, so we can ignore those. So this would be 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial over 3 factorial, and then we expand the other one, 2 times 1. 3 factorials cancel, 2 cancels with 4, but there remains a factor of 4 in the numerator. And so what we'd be dealing with is 9 times 8 times 7 times 6 times 5 times 2. So if we did that in our calculator, 9 times 8 times 7 times 6 times 5 times 2, we end up with 30,240. So there'd be 30,240 unique ways for Sheila to arrange the textbooks on her shelf, or actually just the books. I'm pretty sure Hop on Pop is not a textbook. Arrangements. Okay, last example. How many different arrangements are there for the letters of Indiana? So let's start by saying, okay, how many letters are there in Indiana? There is 1, 2, 3, 4, 5, 6, 7. Of the 7, so we know we're dealing with 7 factorial, but I's there's 2, N's there's 2, D there's 1, and A there's 2, right? And this adds up to 7? Yes, that's 7. Check. So then what we want to say is we want to say, okay, we need to divide out the repetition of the I's, the repetition of the N's, and the repetition of the A's, giving us 7 times 6 times 5 times 4 times 3 times 2 factorial. One of these we get to say 2 factorial, the other 2 we're expanding. So 2 times 1 times 2 times 1. The 2 factorials cancel. The denominator, we're left with 2 factors of 2, which would be 4. So that would just cancel with that 4 there, leaving us with 7 times 6 times 5 times 3. So this would be 21 times 30. Looks like we're going to have 630 different arrangements of the letters of Indiana. So remember what that is. It's just like taking the letters and just putting them in any order whatsoever, creating weird 7-letter things. This has been an example of looking at factorials with repetition. Thank you for stopping by.